Hey guys, welcome to Unit 8 Notes B. Hopefully you're familiar with the pH scale from Honors. We're going to review those calculations a little bit, but we're also going to look at something kind of new called the KW. So the pH value can be used to compare to a general pH scale, which again should be fairly familiar. The lower the numbers, the more acidic, and the higher the numbers, the more basic. So we can actually use this to kind of indicate whether it's acidic or its acidity, or whether it's basic, which is kind of a new-ish term. A basic solution would be an alkaline solution. So they say, as opposed to acidity, this is alkalinity, or how basic a substance would be. In other words, how high the pH is. The reason that we can use the pH scale, aside from just the general idea of wanting to standardize this process, is because we want to relate it to the hydrogen ion concentration, which is very small, and we're about to look at how that logarithm scale actually works. So about that pH scale, what in the world does the P even stand for anyway? Well, it kind of means power, but that's English, and the English didn't come up with this term. It actually originated in France, and so pouvoir, pardon my pronunciation there, is French for the term power, and it's basically identifying that logarithmic function of the pH scale. The normal range of the pH scale goes from 0 to 14, and so what we're seeing is a power of 10 changing 14 different times throughout this pH scale to represent the change in the hydronium, or on the flip side, hydroxide concentrations. One thing to note is the 0 to 14 is not an absolute cap. Those are just the largest whole numbers that we're going to see, but it is possible to get a little bit below a pH of 0 or a little bit above a pH of 14. We actually did one of these examples in Honors Chem where we had the pH outside of this range. So hopefully this is a familiar formula. The pH is equal to the negative logarithm of the hydrogen ion concentration, or you could also say the hydronium ion concentration, right? Because of how autoionization works. So either way, we're finding that concentration, we take the logarithm of it, we make it negative, we find the pH. So as it turns out in IB, we are mostly actually given the pH, and we're looking for the hydrogen ion concentration. So let's go ahead and kind of derive this second formula from the first one. First, I would go ahead and flip the signs, then I'm going to find the antilog. So the hydrogen ion concentration is equal to 10 to the negative pH, or the antilog of the negative pH. So this is a more useful formula, and we'll go directly to that formula most of the time. Now let's touch base on what that logarithm function actually looks like. When we say that there's an exponential function, it could be exponential in lots of ways. It could be raised to the second power, third power, and whatever. This is actually raised to the 10th power. It's a normal logarithm. So as the pH decreases, the hydrogen ion concentration is increasing by a factor of 10. And so that's what we see in this graph here, that as our hydrogen ion concentration is decreasing by a factor of 10, our pH is increasing. And keep in mind that the higher pH actually makes it more basic. So less hydrogen ion concentration, more basic the solution. Now let's look at an IB style question related to pH. Although the math is exactly like Honors, the questions are a little bit different. This question is asking us to compare two different solutions, one of a pH of 3 and one of a pH of 5, and asking how that hydrogen ion concentration changes. So the first thing that I want to do is calculate the hydrogen ion concentration for each pH. So using the formula where the hydrogen ion concentration is 10 raised to the negative pH, or the antilog of the negative pH, we can find the concentrations. For the pH of 3, it's 0.001, and for the pH of 5, it's 0.00001. So there's 2 extra zeros in the pH of 5. It is that much smaller by 2 decimal places, which makes it 100 times smaller. So if it's 100 times smaller, this is how we would present our final answer. That the hydrogen ion concentration is 100 times smaller in the pH of 5 than in the pH of 3. And again, you can tell that because the decimal place is 2 places further. So it's 2 zeros. So 100 times smaller, 100 having the 2 zeros. It kind of shows what you are looking at in terms of factors of 10-fold changes. So here's their work. If you don't like jumping into the formula where you just find the anti-log of the negative pH, you could use the original formula, plug in, and then you start unraveling it. You change the sign, and then you find the anti-log, and basically you still end up with the -3, the -5, which is a factor of 100. Next, we'll review sig figs. So for a logarithm, the rule is that the number of decimal places in the log is equal to the number of significant figures in the answer. So if you're finding the log of a number, those sig figs become decimal places. And if you're going backwards for antilog, the decimal places would become the sig figs. So specifically applying that rule to this application of finding the pH in the H plus concentration, the significant figures of the concentration are going to equal the decimal places for the pH. And one weird little thing I just always seem to kind of latch onto and remember is that you cannot have a pH without decimal places in order to have a workable number. And that kind of helps me remember, well, if there's no decimal places, there's no sig figs. You can't have sig figs and have an answer. That doesn't make any sense. So no decimal for the pH doesn't work. You're always going to have a decimal for the pH because those decimal places become the significant figures of the concentration. So I hope that helps. Now we're finally going to dive into something brand new. So we're going to look at the equilibrium constant for the auto-dissociation of water, or the auto-ionization, I should say, of water. So this is a reaction we've looked at before. We're only going to look at the first step of the reaction, which is the rate determining step. And so we're going to look at how water would dissociate into hydrogen ions and hydroxide ions. We're not going to worry about then that the hydrogen ion would combine with water to form hydronium and then the net reaction. We're looking only at the rate determining step here because we're looking at an equilibrium concentration. So if I'm looking at equilibrium concentration, I'm going to do product up top over reactant on the bottom. And this is the basic setup for our equilibrium expression. But there's a catch. Remember that equilibrium constants do not include pure liquids or pure solids. So the water's out. Now that I have Kc equals the hydrogen ion concentration times the hydroxide ion concentration, I want to make a parallel. Because this is specifically looking at the auto-ionization of water, our Kw will be the Kc. That is what we're looking at, is the water's equilibrium constant. We've gotten rid of the actual water because it's a pure liquid, and we only have Kw as the hydrogen ion concentration times the hydroxide ion concentration. So this is an important equation that we're going to be using. Let's add a little bit of detail to why liquids and solids do not appear in equilibrium expressions. Part of the reason is because so little of it ionizes that the concentration is considered to be constant. Now let's take a mathematical look at this. Let's say we didn't get rid of the concentration of water. We let that be part of the Kc expression. In order to solve, we would kind of multiply both sides by the water concentration, and so we would get an equation that looks like this. So now let's think about what the water concentration is actually doing. Well, if it's the same all the time, because there's very little dissociation, that like with sig figs per se, that we have the same number regardless of what's happening, then what is the point of multiplying by it all the time? So if we have such a negligible dissociation, that concentration is constant, then that multiplier does nothing. And so we just have Kc is equal to these ion multipliers. And remember, this was for the autoionization of water, so Kc we allowed to be Kw. So what we've basically derived is that Kw is equal to the hydrogen and hydroxide ion concentrations multiplied. So this simplified version of the formula is essentially what we will be using. Kw is equal to the hydrogen ion concentration times the hydroxide ion concentration. We can continue to derive more formulas from this because we have experimentally determined that at room temperature, or the thermodynamic constant of 25 degrees Celsius, Kw is 1 times 10 to the negative 14th. So we can use this to kind of input into the prior formula and figure out what each concentration might be. So the formula we just got was that Kw equals these ion concentrations multiplied. Well, in pure water, those concentrations are equal. So if I let X equal one of the concentrations, X would equal both of the concentrations. And so basically Kw would be X squared. Well, if I want to solve for X, then I would square root both sides. So basically, either concentration, the one in particular we're interested in being the hydrogen, of course, would be equal to the square root of Kw. So for pure water, the square root of the Kw of 1 times 10 to the negative 14th is 1 times 10 to the negative 7th. And then keep in mind that the ion concentration was 10 to the negative pH, which allows us to pull out that neutral pH of 7. Look at the sig figs also. 2 significant figures in the concentration, 2 decimal places in the pH. Let's move on to the temperature dependency of Kw. Keep in mind that the equilibrium constant, K, only changes based on temperature. It is completely temperature dependent. So it's important to know that the dissociation of water that we have here is an endothermic process, meaning the heat would be on the reactants side. We'd have heat and water producing a dissociation of the hydrogen ion and hydroxide ion, and that's because we need to break the bond. So that's something we've talked about before, that breaking the stability of that bond requires energy. So it's endothermic. So if I increase temperature, that's like increasing the heat on the reactant side, and that's going to produce a shift to the right, a right shift, which in turn is going to increase the value of K. Keep in mind that K is products over reactants. And so if I shift to the right, I'm making more products and I'm using up those reactants. So if I take a larger number and I divide it by a smaller number, I get a larger answer. So I get this increased K, the increased value of Kw as temperature is increasing. This next part is a little bit weird. Stay with me. As my equilibrium constant is increasing, that is because, again, I am shifting further to the right on the equilibrium. So those products of the hydrogen ion and hydroxide ion concentration are increasing. As I increase the concentration of H+, that makes it more acidic, right? And so that's going to then decrease the pH. And so pH is going to decrease as I make more H+. But the catch is I'm also making more OH. And so in reality, on the pH scale, those both are increasing. And so you can't really say that the water is becoming more basic or more acidic. But if you look at a little more depth, a little more decimal places, we will actually be able to see changes in the pH, but it's still going to be very, very close to neutral. Let me preface this discussion about the table with this is not correct scientific notation, but more importantly, we are looking at its relation to a pH of about 7. And so the numbers aren't in correct scientific notation because we want to keep the exponent constant at a -7. So now, if we are going to increase the temperature as we go down this table, what we would be doing in turn, since K is temperature dependent, I'm shifting it further to the right as we just discussed, making more products, then I would be increasing the K value. So we see that as we increase the temperature, we also increase the KW value. So as we go down here, we see larger and larger values for K. What is it doing specifically to the hydrogen ion concentration? Well, as I shifted right, that was increasing the product concentration, right? And so we're also seeing an increased H plus concentration. As we go down, we see slightly higher numbers. Keep in mind this is still to the -7. For observable purposes, it still appears neutral, but there is a change in the concentration, and therefore, of course, there will also be a change in the pH. As we have more and more hydrogen ions, it becomes more acidic, and therefore the pH is going to decrease. More acidic solutions have more low values for the pH. So as we go down the pH, we are decreasing our concentration. So a higher temperature will increase the KW and the hydrogen ion concentration, but decrease the pH. One last useful relationship. If the hydrogen and hydroxide concentrations are equal, then that is the very neutral exact pH of 7. If I have more hydrogen ions, it is more acidic, which goes with a lower pH. And if I have more hydroxide ion concentration, that is more basic, aka more alkaline, and that's going to have the higher pHs. So you don't actually have to calculate the pH in order to determine its acidity. You can actually just compare the ion concentrations. And if you have more hydrogen, it's acidic. If you have more hydroxide, it's basic. Now let's try an example like that. In this example, we're given the hydrogen ion concentration, and then we're asked for hydroxide ion concentration, and then a determination of whether it's acidic, neutral, or basic. So I want to calculate hydroxide and then compare the two concentrations. Next, we'll use the formula where the ion concentrations are assumed to be multiplied in order to be equal to the Kw, and knowing that the Kw is 1 times 10 to the -14th, we can basically set up this formula, and then the next step is going to be to plug in the hydrogen ion concentration and solve for hydroxide. So when you plug in and do that division, you get 2.17 times 10 to the -7th molarity. Now our next step is to determine whether it's acidic, basic, or neutral. And to do that, we need to compare the concentrations. So now we want to ask whether the given hydrogen ion concentration of 4.60 times 10 to the -8th is greater than, equal to, or less than the calculated concentration of 2.17 times 10 to the -7th for the hydroxide. And if you look at the exponents, we can see our answer. The 2.17 is greater, so we would have our sign facing that way, meaning the hydroxide is the winner, and therefore it is basic since the hydroxide ion concentration is larger. More of a basic ion leads to a more basic solution. Now, spinning off that same question, with this same hydrogen ion concentration, what if the temperature was 37 degrees instead of the given 25 degrees? So first we have to figure out, was the temperature increasing or decreasing? Well, if we were given 25 degrees Celsius and now we're asked about 37 degrees Celsius, that is an increase in temperature. Temperature is going up. So now we'll go back to the whole idea that the process is endothermic, and so if you increase the temperature, then it's a shift to the right, which would favor the products, one of which is the hydrogen ion concentration. And the pH then would be inversely proportional to the ion concentration. More hydrogen ions in solution, more acidic, and so the lower the pH. Next, I want to derive another formula, and this beginner formula should look familiar, that the POH is equal to the negative log of hydroxide, just like the pH is equal to the negative log of the hydrogen or hydronium concentration. So we've looked at a couple different formulas, but it can be a little confusing about how multiplication can turn into division, and it comes from the rules of logarithms. The ending formula I want to go ahead and jump to is something that we've already used in honors, and that's the idea that the pH and the POH should add up to 14, and that's how we can calculate one from the other. And it actually all starts with the equilibrium expression, something you probably didn't realize in honors. And we've already explained why we're leaving water out of this expression. The Kw is equal to the multiplication of these ions. So we can kind of derive the formula that we used before, where 14 is the sum total, by doing the negative log of either side and then applying the logarithm rules for multiplication, which brings in our addition. And so that eventually leads to the pKw equaling the pH and the pOH. Keep in mind that negative log of H plus is pH, negative log of OH is pOH. Those are their own formulas. We can put this all together using the Kw of water, and we can get that 14 equals the pH plus the pOH, even though 1 times 10 to the negative 14th was equal to the concentrations times each other. And that's all from the rule of logarithms. Now I want to look at how these four things can kind of complement each other, and we can kind of figure out one from the other. There's a scale for all of them. Let's start with the most acidic substance possible. Let's say a pH of 0. That would have the maximum actual hydrogen ion concentration and a minimal hydroxide ion concentration. And so if we calculated the pOH, we'd get the high number of 14. Now as we start to increase the pH, kind of hanging on to the pH scale as the basis for our acidity determination, if we go all the way up to the pH of 14, now I have very low concentrations of hydrogen ions. Makes sense because it's very basic, which would mean in turn that it has a lot of hydroxide ions and a very low pOH. So these systems are very complementary in the sense that the more acidic it is, the less basic it is, and vice versa. And so that can tell you a lot about all four things: hydrogen and hydroxide ions, pH, and pOH. If we know one, we can find the other three. So before we wrap up with one last example, these are the basic formulas that are going to be useful. Well, them and their derived counterparts. I do think that jumping straight to this version of the pH formula is going to come in handy a lot in this unit. So you just take the antilog of the negative pH to find the hydrogen ion concentration. So we have the pOH formula, the pH formula. Then we have the fact that if you multiply the ion concentrations, you should get Kw, which has been determined to be 1 times 10 to the negative 14th. And then we also have the summative formula here that if you add the pH and the pOH, you should get 14 using logarithm rules. So to wrap it up, I want to prove that if you're given one thing, you can find the other three things using any combination of the formulas. So I want to use what I think is the quickest to kind of show you a train of thought that would speed things up. When you're given pH, it's very easy to find pOH. It's essentially the complement to 14. 14 minus the pH will yield our pOH, which is going to be 11.10. Next, I want to find my ion concentration by doing the antilog of the negative, either pH for hydrogen ion concentration or pOH for hydroxide ion concentration. So I'm just going to plug in the values I already have for pH and pOH. So the hydrogen ion concentration will be 10 to the negative pH, and that comes out to be 1.3 times 10 to the negative third. Because we're solving for concentration, I'm going to use the molarity units, or in IB style, that would be mole dm to the negative third. For the hydroxide ion concentration, I have 10 to the negative pOH, which turns out to be 7.9 times 10 to the negative 12th. And then again, the units molarity of moles per dm cubed. And actually, as I do this, I realize I have the sig figs wrong on that last one. So let's talk sig figs. The pH decimals should be the hydroxide ion or hydrogen ion concentration sig figs. So I'm good here where I have 2 decimals, so 2 sig figs for hydrogen, but I also have 2 decimals for the OH, so I should have 2 sig figs. So I don't know why I wrote this 0, but it should just be 7.9 times 10 to the negative 12th moles per decimeter cubed. And again, any combination of steps works perfectly, but this is just the fastest way. Look at the complement and do your anti-log of the negative pH or POH, and you'll get to your concentrations pretty quickly. So that'll do it for today. That is the end of Notes B. Next, we're going to get into Note C, and we're going to take a much closer look at the equilibrium constant. We'll see you there.